By definition, an operating system is a software that is used to manage the hardware and software resources within a computer system. So let's take a look at some examples of these resources. A good example of software resources would be the applications that are installed on your computer system. For example, the web browser, the media player, the games that you've installed on your computer system. The different hardware resources that need to be managed by the operating system include the CPU, the memory, and by memory we mean the RAM, the storage devices, and the I/O devices. Before I proceed further with how the operating system manages some of these resources, let me explain a few very important concepts. When we want any application to be present in our computer system, we download it and install it on a hard disk drive. I've just shown a few different types of applications that can be downloaded and installed on the hard disk drive. The web browser would be an example, the different games that you might want to download and install, the media player that you would download and install on your computer system. So these are all applications that you want to download and install on your computer system. What is important to realize is that these applications cannot run on your computer system directly from the hard disk drive. These applications need to be loaded into the RAM before they can run on the computer system. So if an application lying on the hard disk drive wants to execute on the computer system, it has to be moved from the hard disk drive. It has to be moved all the way to the RAM, right? But this decision on whether this application can immediately be moved to the RAM or should it wait for a certain period of time before it can be moved to the RAM, this decision is made by a software called the long-term scheduler. Now the long-term scheduler is part of the operating system and it decides when that application which wants to execute on the computer system can be moved into the RAM. Okay, let's go through some notes on the long-term scheduler. One, that it is part of the operating system. Secondly, when an application program wants to run on the computer system, the LTS decides whether the application program can be loaded immediately into the RAM or it must wait for a certain period of time. Please also note that once inside the RAM, this process is entered in a queue where there are other processes that are also ready to run on the CPU. So this process is entered into a queue because there are other processes before it that want to run on the CPU. In a normal desktop, there is typically no need of a long-term scheduler because you don't need to plan that way. You don't want to delay any application or any program from running on the computer system as such. On the other hand, this kind of scheduling by the long-term scheduler would be needed in a real-time operating system, because in a real-time operating system it is critical for some processes to complete their execution within a given amount of time, and the LTS would not allow more processes to be added into the system, to be loaded into the RAM, because this could slow down the other processes. Therefore, if a new program wants to run on a real-time operating system, it may face some time delay before it is allowed or before it is loaded into the RAM. At this point in time, I would like to differentiate between a process and a program, because a process and a program are two different things. Okay, let's imagine a situation where the user clicks on a web browser icon. So when he clicks on that web browser icon, the program code for the web browser gets loaded into the RAM. So this is where the program code gets loaded. Okay, so this is the program code, right? So this is where the program code is loaded. Okay, but this is not sufficient to run on the computer. Obviously we know that this program code is going to need some piece of data that it's going to process, and since we are considering the example of the web browser, it most likely is going to need some sort of HTML file that it may need to process. So that HTML file will also need to be present in the RAM, so that needs to be loaded into the RAM also. So let's assume that this is where we are going to be loading our data, right? The file that the HTML file that the program code is going to be working on. So now we realize that it's just not the program code that's enough to run on the processor. We need the data also, right? In fact, what runs on the computer system is just not the program code. It is much more than the program code. It is called a process, and a process has multiple parts. The process is made up of many parts, including the program code, the data that this program code is going to work upon, the stack data structure. A process needs a stack data structure, so some space in the memory is going to be reserved for the stack data structure. So some space in the memory is going to be reserved for the stack data structure. Okay, let me explain why a process needs a stack. If we take a look at this piece of code, this part here is our test code, right? This is our test code. So these are the instructions that are going to get executed. When we take a look at the first instruction that's going to get executed, then this instruction is basically a procedure call. A call is being made to this procedure, so the control from this line is going to get transferred to the procedure, and now the instructions within the procedure are going to be executed. So this procedure is going to stay active for some time, but once this procedure is complete, once the instructions inside the procedure have been executed, we need to resume from where we left off. So now the control needs to go back right here. So somehow the process needs to keep track of which line the procedure was called from, right? So this is where the stack comes into play. Before making call to procedure, store location of instruction onto stack. So now that you've stored the location of the instruction onto stack, the control can be transferred right to the procedure. The procedure can execute, and once the procedure is done with its execution, we look back at the stack to determine what location was saved there. We find out that location, and so we resume our program code from that point onwards. So a process includes the program code, the data, the stack data structure. A process also includes something called a heap, right? And we are not going to look deeper into the details of a heap, but heap is used to assign runtime memory allocations. So once the process is running, if there is need for further memory, if the process requires further memory or some variable that needs a newly created variable that needs to be stored somewhere, that is when the heap comes into play. So some part in the RAM will be required for the heap, right? It is also important to know the current state of the process, and for that the register values are very helpful. For example, the value of the program counter right now, if the process is running on the computer, will tell you which next instruction needs to be fetched. The value in the accumulator is also very important for the process. For example, some instructions later on in the program code might want to use this value of the accumulator, right? So the register values are important because they are helpful in maintaining the process state. So all of these are part of the process, right? But besides these, the register values are also part of the process, the register values. And it is also possible that this process that is running on the system right now might request some resources like network connections, because this process wants to connect to some other computer over the network to request some resource from from that other computer, right? So so it might request some network connections, right? So to define the process completely, we would require the register values to be known, and the process also has some network connections that are open. So the operating system needs to keep track of the entire process, and for that it's going to need the stack, the heap, the data, the program code, the register values, and the network connections that are active for the process. So technically, I hope you can now understand that what runs effectively on the computer system is much more than just the program code. You need the whole process. You need to keep in mind the picture of the process that's running rather than the program code itself.